Thank you very much. First, lots of thanks to Ali and all the organizers for this opportunity. It's a great pleasure to be here. So I'll try to compete with afternoon siesta by telling you about some exotic states which are possible in quantum materials. So why not magnetic monopoles in electromagnetism? At the classical level, only the equations of motions, the Maxwell equations, are relevant. And there is absolutely no problem in adding, I have to find here, in adding a magnetic current with a magnetic charge to the homogeneous Maxwell equations. F dual is the dual electromagnetic tensor, which exchanges electric and magnetic field. And originally, the founding fathers did not include magnetic monopoles simply because they never observed ones. So fast forward to the 30s, Dirac, he asked the question just after the development of quantum mechanics, he asked the question, what about monopoles in quantum mechanics? And of course, in quantum mechanics, the equations of motions are no more enough to describe the system. You need to formulate a local action, local in terms of the fields. So when you want to formulate a local action for electromagnetism, you have to include a gauge potential A. You cannot formulate a local action only in terms, in terms of the electromagnetic fields. And this, naively at first sight, can cause a lot of problems because you have strong singularities. However, Dirac showed that if his famous quantization condition is satisfied, the product of magnetic and electric charge is an integer multiple of 2 pi. There is still no problem, and you can have quantum magnetic monopoles. And magnetic monopoles looks like this. There is an infinitely thin and long solenoid bringing in magnetic flux from infinity. And this magnetic flux flows out radially symmetric at the location of the magnetic monopole. And Dirac showed that if this quantization condition is satisfied, this solenoid, this infinitely solenoid, is nothing else than an unobservable coordinate singularity. And today it goes under the name of a Dirac string. So if it's here and you don't like it here because you have some physics going on here, by a just gauge transformation, coordinate transformation, you can bring it wherever you want. So it's no physical, and physical is only the endpoint of the magnetic monopole. Only problem is that the presence of this magnetic string, this Dirac string, forces the possible gauge functions, lambda, here, to be periodic under integer shifts of 2 pi. This is familiar to you in vortex physics. To have a vortex, you need the gauge functions to be circles, compactifier on a circle. And this means that the gauge group that you have is not the group of real numbers, but it's the compact U1 gauge group. U1 is homotopically equivalent to a circle, S1, and a circle and R are locally the same, but not globally. And the difference in the global behavior is just the presence of magnetic monopoles, which are the singularities at the endpoints of the Dirac strings. Singularities, as usual, are no good in physics. They have to be hidden. There are 2 ways to do that. The first was originally proposed by Toft and Polyakov, is to hide the singularities by obtaining the compact U1 gauge group by spontaneous symmetry breaking from a very larger compact gauge groups. For example, the grand unified gauge groups SU5 or SO10. And then you have a magnetic monopole which has a core in which the grand unified X and Y bosons are excited, a core in which you see the electroweak W and Z, quarks, and so on, and only at the very, very largest distance you see only the magnetic field. No more singularity because spontaneous symmetry breaking resolves the singularity within this course. Only problem is such magnetic monopoles are extremely heavy, 10 to the 16 giga-electron volt, and they could have been produced only in the Big Bang, and they've never been observed despite 40 years of search. However, there is another way to hide the singularities. This was pointed out originally by Polyakov, is to formulate the theory on a lattice. If you formulate the theory on a lattice, you can put the monopole and the Dirac strings in between the lattice points. So in the physical lattice, you don't see anything anymore. The singularities are hidden away among the lattice. This has led us, Cristina Diamantini, Valery Vinocourt, who are in the audience, and myself, to propose that much lighter monopoles could be realized in quantum materials, and especially quantum materials which are granular in structure. A granular quantum material is essentially a lattice. And again, the monopoles can be hidden among the granules, and we see the effect, and we can see the effect of these monopoles on the granules. This is the new proposals that we made 4 years ago, and let's focus on this one. So, quantum matter. Quantum matter, charged quantum matter is what I will consider always. Is generically described by an action which has a matter part, the coupling of the current to the electromagnetism, and the usual Maxwell term. So formally, at finite temperature, the integrals here have to be defined. The time integral has to be defined on Euclidean time, compactified on a circle of radius 1 over the temperature. But to be simple, for simplicity, today I will just consider 0 temperature. So I have just an integral over Euclidean 4 space. You can now formally integrate out the matter degrees of freedom to obtain what is called an effective action for the gauge field alone. This is the same term here. And then you have quantum corrections that come from the integration of the matter fields. If the matter fields are quadratic, then of course this is trivial to do by Gaussian integration. If they are not quadratic, then you have to do the usual loop expansion in perturbation theory. The behavior of the system is then described by the induced current, which is called the electromagnetic response, which is the functional derivative of the effective action with respect to the gauge field. Here an example of this formalism, superconductors. For superconductors, the effective action here is just a mass term for the photon, A mu, A mu. By functionally deriving with respect to the A, one gets the induced current, which is linearly proportional to the gauge field. And by taking time derivatives and the rho, you get the familiar London equation. So this was just an example. So now let's focus on insulators. What is the effective actions for insulators? The effective action, 0 temperature for insulator, is just the same Maxwell term we are used to, just with a different coupling, a renormalized charge affecting coupling, and with a velocity of light which is now determined by the dielectric constant and the magnetic permeability of the system. Suppose now that we have a granular structure, an emergent structure. Then the system looks like this. You have islands which are separated by a typical ultraviolet cutoff L. Then, of course, this action has to be formulated in a discrete way. So we sum over the island places with multiplying the Maxwell term by the cutoff to the force. And of course, there are 2 ways to do that. Once you have emergent granularity, you can discretize the action, the effective action naively, or you can take, and this corresponds to having a non-compact gauge group R, or you can take the compact gauge group U1, which means that the actual electromagnetic fields E and B are periodic under shifts of 2 pi. You see that by developing the cosine here, the first order term is the same, but the two actions are very different globally. Indeed, you can formulate the compact action in Villain form instead of cosine. This you're probably very familiar. You introduce dynamical integer fields on the plaquettes of your lattice, this m mu nu, and then you sum over f mu nu over a mu and m mu nu, and you see that by this combination, the periodicity of this combination is guaranteed by these integers. So this is the Villain form of the compact action. Now comes the important point. These guys here satisfy the usual Bianchi identity or homogeneous Maxwell equation. This means the divergence of B is equal to 0 essentially. But this integer that appear here because of the compact nature of the gauge group there is absolutely no requirement that they satisfy that the divergence has to be 0. And this means that the overall magnetic field formed from this combination can have monopoles of strength 2 pi over E square effective. So you see that when you have emergent granularity, magnetic monopole in the effective action appear naturally in quantum matter. Actually, one should eventually ask why not. Fine. So let's now focus on some concrete example of granular materials, quantum materials. Here is the first one, just to introduce the subject, which you are surely familiar with, is Josephson junction chains or granular quantum wires. So here is the wire. This is space. These are the granules of superconducting islands. Each is characterized by a particular phase of the order parameter there. On the vertical direction here, I depict Euclidean time. So this is pictures of the wire taken at different instant of time. And now what can happen is tunneling events, which go under the name of quantum phase slips. And these are events in which one particular phase from one moment of time to the other makes a 2 pi flips. This is a tunneling event. In field theory, it's called an instanton. And the effect of these instantons is well known. It's to induce the resistance in the superconducting metal, in the superconductor, in the one-dimensional superconductor, which becomes essentially a metal. They induce an ohmic relation between charge and potential. Okay, so this is a first example of a granular material. We will not be interested mainly in one dimensions, but rather in 2 dimensions. So let's consider the natural generalization of this. This is Josephson junction arrays or granular superconducting fields. Here we have the same physics. Now on the plane, the arrangement of the droplets of superconductor is now 2-dimensional. Each is still characterized by a phase of the order parameter, but we have now the possibility of new configurations. Suppose you have 4 addition droplets here in which the phases are arranged like that. Then the phase here makes a circulation of 2 pi, which means in the middle of this arrangement of superconducting droplets, you have a vortex. But this is not an Abel-Coser vortex. This is a Josephson-type vortex. You see, it has only gauge structure if you want. There is no normal state. Okay? There is no normal state because it forms in a granular material and not in a homogeneous material. And because of this, dissipation becomes a subdominant effect. This can be verified experimentally. There is a very, very high degree of duality between charges residing on the islands and this type of Josephson vortices residing in the middle of the islands. And one thing that is almost always forgotten in the literature on this subject is that once you have this type of vortices, you have mutual statistics with the charges. If a vortex goes around the charge on an island, it acquires an Aharonov-Kasher phase. If a charge goes around the vortex, it acquires an Aharonov-Bohm phase. And this cannot be neglected. They have a huge effect. Okay? This is why what I'm talking about now has been almost missed in the literature. So it is actually the competition between the charges on these islands and the vortices in the middle which drives the famed superconductor to insulator transition. 3 phases have been observed. The superconductor is when global phase coherence is established. All the phases point in the same direction. There are no vortices. There are 2 other phases in the system, the Bose metal, when the bulk is completely frozen by this mutual statistics interaction, and there is conduction only by edge modes. And then there is the superinsulator, which will be the focus of the next slides, in which you have a proliferation of vortices. Both these 2 new phases of matter have been first proposed and predicted by myself, Cristina Diamantini, and Pasquale Sodano back in '96. So we had a one-dimensional chain. We had instantons, phase slips. Are there things like this in 2 dimensions? Yes, there are. Suppose you have here the granular material or the Josephson junction array, and suppose you have a vortex circulating as I just pictured in the slide before. So a vortex 2 pi sitting here in this plaquette. Now, here again, I have in the vertical direction the Euclidean time, and we have now a possible configuration in which this vortex here does not exist anymore on this horizontal plaquette in the next time, because all the magnetic flux flows out in the vertical plaquettes. Okay? So the vortex sits here for infinite time. It's just static. Infinite time means static here. And at a certain instant of time, it just flows out horizontally, and there is no more vortex. So this is a tunneling event between 2 topological sectors. 1 vortex, 0 vortex. And the flux goes out in Euclidean on the vertical Euclidean plaquettes. So if you now look exactly what this event is, this static vortex that goes down to infinity because it's static is nothing else than a Dirac string. And the event which is in the middle here is a magnetic monopole. It is actually a non-relativistic magnetic monopole because the flow is only on the plane. There is no flow up and here, but it's still a magnetic monopole. So the instantons in 2 dimensions, if you want the analog of phase slips in 2 dimensions, are magnetic monopoles. What about 3 dimensions? In 3 dimensions, this Josephson vortice is living between the droplet of the granular material become one-dimensional extended object. And of course, there is now nothing preventing these one-dimensional vortices, Josephson vortices, to be open at their endpoints. And the 2 endpoints are simply monopole, anti-monopole pairs. And now 2 possible configurations exist. If the vortex, these Josephson vortices have tension, then the typical configurations are small dipoles. So no magnetic monopoles, monopoles are suppressed, you just have dipoles in the system. However, if these Josephson type vortices become tensionless, then there is no energy price to pay if you pinch this vortex here, you bring it to infinity, and you bring it back to the anti-monopole. So these lines become Dirac strings, and you have a Coulomb gas of magnetic monopoles. These magnetic monopoles can then Bose condense, and by Bose condensing, they induce a completely new state of matter, which I will focus on in the next slides. What happens in a condensate of magnetic monopoles? So suppose now that you have, okay, so I will give here a heuristic argument to show you what happens. This can be backed up by very rigorous computations. I don't want to present here rigorous computations because they're quite involved, but I want to give you the feeling of what happens. So suppose, for the sake of simplicity, that you have here monopole currents that come either out of the plane or in the plane. So out of the plane, let's say O, and in the plane X. And now put some anti-charge probe in the plane. So the electric field lines between them will be typically in this region. Now you have an electric field like this, and you have a monopole current perpendicular to the plane. You have a dual Lorentz force. The dual Lorentz force will push down these currents and will push up these currents. That means the dual Lorentz force will polarize the magnetic monopole gas. So that all the out-of-plane currents are above the line joining the anti-charge probe, and all the currents in the plane, into the plane, are below. Now comes the dual Ampere law. The dual Ampere's law tells you that these magnetic monopole currents are surrounded by electric fields. Exactly like a usual current is surrounded by a magnetic field, here a monopole current is surrounded by electric fields. Any place in the plane, this magnetic field will cancel out from all the monopoles. However, if you take this line between charge and anti-charge, here instead they all sum up. So what this gas of monopoles is making is to creating an electric string, an electric flux tube between charges and holes. This electric field, this electric flux tube between electric poles in a magnetic condensate is the exact dual of what you're very familiar with, the Abrikosov flux tube between magnetic poles in a charged condensate. So this state here is which is called superinsulator, is an exact dual of a superconductor. The only difference is that electric field lines can end on poles, contrary to magnetic field lines. So the endpoints here, the electric can reside in the interior of the sample. So we have configuration with charges, anti-charges, or charges holes, which are joined by an electric flux tube. And these are nothing else than the electric equivalent of strong interaction pions. This is the phenomenon of confinement. Indeed, in this phase of matter, Cooper pairs play the same role as quarks do in hadron physics. They are joined by a flux tube and electric string, which amounts to a linear potential with string tension sigma. So no U1 charge is observable for scales larger than the scale of the pion, which is 1 over the square root of sigma. And it means that in large enough samples, this phase will show an infinite resistance, strictly infinite resistance, even at finite temperature. And this is what distinguishes from a normal insulator. There is a phase transition. At finite temperature, we still have an infinite resistance. This is why it's called superinsulator, and it's a dual superconductor. Duality goes farther than this. Actually, like in a superconductor, we have two critical magnetic fields for penetration. We have a Meissner mixed state. We have the same thing here. We have two critical voltages, VC1, VC2. If you apply voltages smaller than VC1, only neutral pions can be excited. No current passes. This is the electrical Meissner state. If you apply a voltage between the two critical voltages, the string is stretched and reaches the sample boundaries. Here, current starts to pass. You have electric flux penetration. This is the mixed state of the superinsulator. Finally, if you apply large enough voltages, the whole state of matter is destroyed. Superinsulators have been observed by many groups in several materials. I show here the typical granular structure in a titanium nitrate film. So this is the structure of the superconducting gap. So you clearly see various granules, red where you have high gap, blue where you have zero gap. In the same sample, correspondingly, hyperactivated resistance has been measured. So here you see the sheet resistance as a function, sheet resistance in logarithmic scale as a function of 1 over the temperature, so that the straight line corresponds to the usual activated behavior, Arrhenius activated behavior. You see here a clear deviation. This is called hyperactivation, and it can be shown that this scaling, that these curves here scale to a Brzezinski-Kosterlitz-Thoulez phase transition, which diverges at the finite temperature. And this means below this temperature, the resistance becomes strictly infinite. In the IV curves, so current as a function of voltage, we see two kinks, which corresponds to the Meissner state and the mixed state. So here you see, for example, the red curve, the first king, the second king, or here in the red curve, very clear, this is VC1, VC2. So this is perfect confirmation of the existence of a Meissner and a mixed state. Finally, another very interesting phenomenon, the monopole gas not only creates a linear interaction between charges and holes, it also screens the Coulomb interactions on very, very short scales. So we can have this situation here, which is the linear potential, the string between charges and hole is taut. This is the one that gives you the hyperactivated behavior I just showed. But we can have a situation in which the string is loose, so the charge and anti-charge are very near, sufficiently near that the linear interaction is not felt, but neither is the Coulomb interaction because it's screened on even smaller distances. So on these distances here, charges and anti-charges, charges and holes in condensed matter language are essentially free. This is the phenomenon which is called in field theory asymptotic freedom. It means that, and it's realized also in strong interaction ions, the quarks inside the pion are free. And here the Cooper pairs inside these electric pions are free. In an experiment now, okay, so sorry. Strong interaction pions are very small because the interaction is very strong, and there is no possibility of looking inside. But the electric interaction is more weak, so one could imagine that the size of these pions is large enough so that one could measure the inside by taking small samples. And indeed, this is the case. Here you see that if you take large samples, you see again the hyperactivated behavior much stronger than the usual activated behavior. But if you take a smaller sample, if you go down to 0.2 millimeters, you have a metallic saturation, and this means you are inside the scale, the string scale, and you see asymptotic freedom. You see just free charges. The interaction potential between charges and holes can also be measured directly by dynamical relaxation. You will hear a lot about this if you go to Alexei Mironov talk. So I don't want to spoil all the details of the experiment, but here the theory part. So what you do, you measure the delay for current passage as a function of an applied voltage. Actually, I scale it with the difference of applied voltage minus the threshold. Again, you see here, take the red sample, for example, you see clear here two different scalings, and this corresponds again to the Meissner and mixed state. The jump corresponding to a scaling exponent minus 1/2, it's for all samples, you see it's minus 1/2, corresponds to jumps to voltages which jump from the Meissner to the mixed state. The jumps from the Meissner state to the normal state corresponds to -3/4. Now, suppose you have this linear potential which corresponds to an attracting force, a constant attracting force, charge times the string tension, which is the threshold divided by the sample length. And now you apply a repulsive interaction with a constant voltage V, and so the force is V divided by the sample length. So the acceleration in the center of mass is the reduced mass times the total force, which is this minus this. V minus V is critical, the threshold. And high school physics tells you that the separation is then a square power of the time. And by reversing this, you get immediately the -1/2 critical exponent. So this measure here is a direct measure of a linear potential between charges and holes in the superinsulating states. Granularity is not confined to 2 dimensions. The same physics has been detected recently in 3-dimensional superconductors, and most importantly, the underdome regime of high TC cuprates is granular. In 3 dimensions, then we have the additional possibility of an even more exotic phenomenon. By a topological effect, there exist excitations called dyons, which carry both magnetic and electric charge. And so we have proposed, here is the new proposal, that, again, the PSEUDOGAP state, this is the typical phase structure of high TC material cuprates, that the PSEUDOGAP state here is actually a condensate of dyons, and that the superconducting dome here is a mixture of a usual charge condensate and the dyon condensates, coexisting mixture. Now, if you take this seriously, you can go through the physics, and it turns out that the existence of magnetic monopoles, of magnetic charge, solves essentially the entire mysteries of the PSEUDOGAP state. I'll give you some examples without going into in detail. So magnetic charge in the PSEUDOGAP state turns, this important point is magnetic monopoles induce statistical transmutation of Cooper pairs. If you bring a Cooper pair near magnetic monopoles, it becomes a fermion. In the PSEUDOGAP state, the charges, it turns out, are symmetry-protected boundary fermionic Cooper pairs. These live on a percolation network of edge states, and since they're fermions and symmetry-protected, they immediately constitute a perfect Fermi liquid, and you have immediately explained the T-square resistance measured in the PSEUDOGAP state. Of course, magnetic charge immediately leads to the observed magneto-electric effect. Magnetic charge very simply explains nematicity of what we heard this morning. Suppose you have the insulating state of a high TC cuprate. It is on the square, on one plane, it is a perfect square antiferromagnet. Of course, then you would expect this famous C4 symmetry, but imagine now that the charge carriers carry not only charge, but magnetic charge. Because it's an antiferromagnet, you have equal spins only on the diagonal, so C4 is immediately broken down to C2. So nematicity is very easily explained. It turns out that magnetic charge can easily explain also the T resistance when an applied magnetic field is applied. Maybe this is a little bit more complicated. If somebody is interested, I can explain it just later of the seminar. And magnetic charge immediately also explains why Cooper pairs cannot be split in the PSEUDOGAP, and so the observation of Cooper pairs in the PSEUDOGAP state. I want to conclude with one particularly important slide about the role of disorder. It turns out that the only role of disorder in the superconducting insulating transition is to tune the strength of the Coulomb interactions. All the phases which are observed, the nature of the phases which are observed around the superconductor to insulator transition do not depend on disorder. So disorder is irrelevant in the renormalization group since it does not influence the nature of the quantum phases. And one thing which is crucial is that all the phenomena which are usually associated with strong disorder, many body localization, etc., like breaking of thermalization, breaking of ergodicity, simply follow from linear confinement. There is no need of disorder. Confinement explains all these phenomena. So let me conclude. This is the takeaway for today. Magnetic monopoles appear very naturally in granular superconductors. A Bose condensate or a plasma in 2 dimensions of magnetic monopoles lead to a new state of matter. Superinsulators, which has been detected in titanium nitrate, niobium titanium nitrate, indium oxide, and niobium silicon films. Disorder is not relevant for the nature of the phases around this superconductor to insulator transition. Finally, a condensate of dyons, particles, excitations carrying both magnetic and electric charge, could explain the entire physics of the pseudogap state. For references, details, anybody who's interested, I refer to the recent book I wrote for World Scientific about all this stuff. I will conclude here. Thank you very much.
Okay. Thank you, Carlo, for the very nice presentation. I went in and out, but I think I have captured some essence of it. Any question? Yes, Vladimir, please.
Carlo, thank you very much for your nice presentation. And in what concerns theory speaks for itself, my question is about a couple of slides, your first slides, which concern experiments which confirmed this phenomenon. I think it was in...
this was the first experiment.
Yes, yeah. Could you kindly provide a little bit more details? There are no references to these experiments. And yes. Second, as far as I understand from the spirit of your theory, there should be really absolute insulator, but in this experiment there is some inclination at this point of the characteristics in Bose.
You mean here?
In Bose. For example, here, what are the physical reasons of this deviation from absolutely vertical jump? There are probably still some elements in this place. Thank you.
So first of all, to answer this is a picture
recording in progress
from the experiment of Tatiana Baturina, Valeri, and Christoph Strunk and collaborators. As a reference, I'm sorry that I didn't give enough references. So, as I said, this is logarithmic scales. So this line here would correspond to a perfectly activated insulating behavior. Now, here you have deviations. Now you can fit these deviation curves. And it turns out, it's not marked here, it turns out they are perfectly fit by the Berezinski-Kosterlitz-Taules formula. If they are fit to the Berezinski-Kosterlitz-Taules formula, it means that there is a finite temperature here at which this curve is strictly infinite. This means that they do go to infinity at a finite temperature. Below this temperature, you have infinite resistance. And the important point is that it's a finite temperature. It's not zero like in a normal insulator. They diverge at a finite temperature. Mm-hmm. And this is the scaling here, BKT scaling, is quite impressive.
Okay, but this, what we see, it's apart from Berezinski-Kosterlitz-Taules.
These curves here are BKT. These are BKT curves.
Yeah.
So they diverge at a finite temperature.
Okay, so it's a combination of two effects, in fact.
Well, it's part, you know. So if you take this plasma of monopoles and you raise the temperature, what happens? And there is a phase transition, which is BKT. So the monopoles get confined, so no more monopoles in a usual phase transition. So you make a transition from a superinsulating state below this transition to a normal insulator above. And these are these curves here.
And this was observed in the experiment.
This was observed in the experiment.
Thank you.
Okay, yes, please.
Just to make sure that I understand. So is your model for the granular superconducting film quantum XY model? 2 plus 1 XY model, is that your model or something else?
Absolutely not. It is a 2 plus 1 gauge theory.
Sorry, 2 plus 1?
Gauge theory, topological gauge theory.
So 2 plus 1 XY model is dual to the Higgs electrodynamics.
It's not a Higgs model, it's a topological gauge theory, which is very different.
Do you have any slide I mean, I don't actually know what the model is.
No, I don't have slides, but you can go to the talk of Cristina Diamantini tomorrow and you will hear all the details about that. Okay? So the statement is exactly the XY model alone is not sufficient to describe all the phenomena around the seat. You need gauge fields.
I mean, my comment is that there are gauge fields in the dual theory of XY model, but that is still not your model,
No.
right? Okay.
No.
I think we're just coming to the, well, Chris, maybe later on, yes?
Yeah, so it looks like a really fascinating scenario. I have a completely different view on pseudogap and cuprates, but I still find it very interesting. My question is slightly related to the previous one. So to get some microscopic modeling for this, would it be sufficient to start from 2D Hubbard, or what would we need? 3-band or even more?
Okay. I didn't have time to go into that. We have a microscopic model, which is very different from the ones you are addressing. The microscopic model we have for pairing leads to a localized pairing and is due to effective magnetic field given by deformations in the materials. So curvature, for example, in material is equivalent to magnetic fields for itinerant electrons, and the spin defects, hedgehogs, and the monopoles at the end are also seen as magnetic gauge fields by itinerant electrons. And so these effective pseudomonopoles are able to bind electrons. And this is our microscopic materials. So in this high TC cuprates, it would be rather the spin hedgehogs that would bind electrons. In graphite, it would be rather curvature defects.
I think we can have just a very short question. I saw a raising hand, but okay. At the back, yes.
Okay, I want to ask you a question about the universality of your results from the quantitative point of view, because all effects are sitting on the small distances, on the granularity and so on. And does it mean that to the answer should enter not only the size of the granule, but for example its capacitance or something else which is related to the precise form of the physics at the small scales? Because in your action you put only the distance, the size of the granular, but if you put it to the zero, you obtain the zero result. So does it mean that you should, what about the universality of the results you presented?
So you should not put to zero this size. It's not a renormalization group, it's a physical size. The actual system decouples into droplets by it's emergent by its own will. And so the scale L is a physical scale which is chosen by the system. It can be different in different materials, so there is no universality.
Okay.
Okay, I think we're running out of time, and let's thank the speaker.